It's mysterious and wondrous. Welcome to the world of relativity. In Lagrangian mechanics, the Lagrangian is the central concept that describes the motion of objects. Knowing the Lagrangian of a system reveals the laws of motion governing that system. This video will derive the Lagrangian in the context of relativity and verify its consistency with the classical mechanical Lagrangian in low-speed environments. Let's start by reviewing the action and the principle of least action in Lagrangian mechanics. In an inertial reference frame, different world lines can connect two spacetime points P and Q, representing possible trajectories of an object moving from spacetime point P to Q. The action is a functional of the spacetime trajectory, with different world lines having different actions. The principle of least action tells us that among all the world lines connecting points P and Q, the one with the least action is the actual trajectory of the object. Assuming that among all possible world lines connecting points P and Q, whether drawn or not, D has the least action, then D represents the actual trajectory of the object. Let's consider this issue from a different inertial frame. After a Lorentz transformation, the positions of events P and Q change, as do the positions and shapes of each world line in the new coordinate system. In different reference frames, the actual trajectories of an object should be the same world line. That is, in Bob's reference frame, applying the principle of least action, the actual trajectory of the object should still be world line D. Action is calculated differently in different reference frames using different coordinate values. How can we ensure that the world line with the least action is the same in all reference frames? One straightforward idea is to ensure that the action associated with any world line remains the same before and after a Lorentz transformation, making the action an invariant. Thus, the actual trajectory selected through the principle of least action is inevitably the same world line. The action is the integral of the Lagrangian over the world line. This raises the question, which Lagrangian function should be chosen so that the action becomes an invariant? In different reference frames, applying the principle of least action should yield consistent results. The simplest way to achieve this is to ensure that the action is invariant under Lorentz transformations, meaning the time integral of the Lagrangian is invariant. It's important to note that the time integral of the Lagrangian is invariant doesn't mean the Lagrangian itself is invariant. This is because dt in the integral is not invariant. What form must the Lagrangian take to ensure the action is invariant? Let us begin by deriving from the differential element of a world line of a particle in spacetime. From previous videos, we have known that the proper time interval of a differential element on a world line is invariant. According to the definition of ddet, it can be converted into a velocity-dependent factor times dt. Dot is an invariant under Lorentz transformations, hence the integral of dtot is also an invariant. Comparing this invariant with the action, we find that as long as the Lagrangian equals 1 minus the square of the velocity squared, then the action is ensured to be invariant. However, it's not reasonable for the Lagrangian to be directly equal to this quantity. To maintain the action as an invariant while ensuring the modified Lagrangian conforms with the laws of classical mechanics at low velocities, further adjustments are needed. The Lagrangian can be multiplied by an invariant coefficient to maintain the action as an invariant. This is the invariant coefficient we have constructed. The first term corresponds to the kinetic energy in the classical mechanical Lagrangian, while the second term corresponds to the potential energy. Firstly, let's look at the first term. M is the mass of the particle, which is a constant, thus ensuring that the action remains an invariant. In classical mechanics, the Lagrangian's kinetic energy part is proportional to the mass of the particle. Therefore, we also make the first term proportional to the particle's mass. Why is there a negative sign here? Soon we'll see that this negative sign ensures consistency with the classical mechanical Lagrangian. Next, let's consider the second term. Phi is an invariant in spacetime, meaning that phi has the same value at a given spacetime point across different reference frames. The Lorentz invariance of phi also ensures that the action remains an invariant. Phi is a scalar field by physical standards. Here, for simplicity, we are just listing the potential energy of a particle in a scalar field. If it were a vector field, the formula would be different, but the overall principle of maintaining the action's invariance before and after Lorentz transformations is the same. G is a constant known as the coupling constant, which indicates the strength of interaction between the scalar field phi and the particle. This is the Lagrangian for a particle in a scalar field in relativity. Here, the part that represents the interaction between the particle and the field needs detailed discussion in field theory. We won't focus on it now. We are only concerned with the first part, or rather, the Lagrangian of a free particle. This part is related to the concepts of momentum and energy of the particle that we are about to discuss. To fully align this Lagrangian with that of classical mechanics, we still need to make some unit changes. Inside the square root, v is measured relative to the speed of light, which equals the conventional speed divided by the speed of light. In classical mechanics, the unit of the Lagrangian is energy. Thus, we also need to multiply the entire quantity by the square of the speed of light. We will explore the momentum and energy of the particle based on this Lagrangian. Before that, we need to first verify that this Lagrangian is consistent with classical mechanics in low-speed situations. Based on Lorentz invariance, we derive a Lagrangian for a free particle as the product of its mass and the square of the speed of light, multiplied by a velocity-dependent factor. Now let's examine how this Lagrangian behaves at low speeds. Does the system's behavior reduce to Newtonian physics? Before we begin, let's first look at a mathematical approximation formula. In Cartesian coordinates, plot the left and right sides of this approximation equation. It can be seen that whenever approaches zero, the graphs of the two lines almost coincide. We can use the method of Taylor expansion from calculus to obtain this approximation formula. When the velocity is much less than the speed of light, we can use this formula to obtain an approximate Lagrangian. This Lagrangian consists of two parts. The first term is the kinetic energy from classical mechanics, which is the Lagrangian of a free particle in classical mechanics. The second term, mass multiplied by the square of the speed of light, is a constant and remains unchanged regardless of changes in generalized coordinates or velocities. The laws of motion for the system are given by the Euler-Lagrange equations. Adding a constant to the Lagrangian does not affect its partial derivatives with respect to generalized coordinates or velocities. Therefore, adding or subtracting a constant from the Lagrangian does not impact Euler-Lagrange equations or the laws of motion. In other words, at low speeds, for a free particle, the system's laws of motion defined by relativistic Lagrangian are consistent with those defined by classical mechanical Lagrangian. This conclusion is an approximation of the relativistic equations of motion at low speeds. As velocities approach the speed of light, relativistic effects become very significant, and the laws of motion will differ greatly from those of classical mechanics.